Today, so we're very happy to have a theoretical talk on sort of a new idea of a quantum spin liquid from Claudio Castelnovo. Yeah, so he's from University of Cambridge, Cavendish Laboratory, and I read his very interesting paper in Nature Physics, but I have to admit I don't completely understand, so that's why I wanted to be educated by him, and hopefully that stir other interests. Particularly, if you can stir future experimental interest, that would be, fantastic, right? Yeah,
we would very much love that. Thank you,
Claudio. It's all yours. Yeah.
Thank you very much. It's a pleasure to give this seminar. Thank you very much for the invitation and the opportunity. I haven't given online seminars for some time. But as I recall, one of the main drawbacks is I don't see the audience, and therefore I have no idea what the reactions might be. There is no need.
People will ask you questions if there are questions. Yeah,
exactly. That's where I was getting. Please ask. Please interrupt, stop me, and everything, because there's no need to get to the very end of the talk. What's important is that what we cover is clear and helps you understand and maybe get excited and interested in this problem. And it's important that it's at the level that you can relate to. And if there's something that is not clear or want me to repeat or anything, just stop me at any point. And indeed, this is a theoretical work with some ideas for experimental exploration that I'd like to explore more. And if anyone has further ideas or would like to take this on from an experimental point of view, but also theoretically speaking, there are lots of open questions that would be very interesting, and I would be interested to discuss. Okay, so this work actually, let me start by mentioning who did it. Was primarily the work of Cecilia Glittum, who was a PhD student in Cambridge, moved on to a postdoc in Berlin, and quickly afterwards got a Marie Curie to go back to her hometown in Oslo in Norway. Together with a postdoc at Cambridge, now a faculty at Zagreb Antrolio. And some of the latest results that I'll mention was done by an undergraduate student who was actually absolutely brilliant. Just finished last year in Cambridge and went to do a PhD in Moscow, Daniil Zitov, and then other collaborators like Christian Batista, Yang Zhang, and Yixing Zhang at Tennessee Oak Ridge, Paul Goddard and is an experimental side, and Prabhakaran on the crystal growth, and then funding from several agencies. So within this talk, that's what I would like to cover. But as I said, I don't have to get to the bottom. Interrupt, I'll keep an eye on time, and we'll see how far we get. I'd like to give a bit of an introduction, very briefly, but on the old questions of resonance valence bond spin liquids, and how the community approached it throughout the years, which typically was via the route of geometrically frustrated interactions. And I will gradually shift the language to show that you can actually induce interesting magnetic correlations, not only from interactions, but also from kinetic energy of charge degrees of freedom dopants in the system. A famous example of that is the Nagaoka effect, which induces ferromagnetism. And the one that I'll be talking about has been dubbed the counter Nagaoka effect, that instead induces antiferromagnetism. And the new area where we took this phenomenon is that of corner-sharing tetrahedral lattices, where something very special happens, which is rare in strongly correlated many-body physics, non-Fermi liquid physics, etc., is where we can find an exact ground state, an RVB liquid state in a frustrated dopant insulator. And I'll explain what all of these words mean. Hopefully, by the point we get to this, it will be clear to everybody. And as I said, we have exact results for 1 and 2 holes, and then we have numerics to explore finite density, perturbative interactions, etc. And what we have found, we think, is potentially a new paradigm to realize quantum spin liquids, not based on geometric frustration, but based on kinetic energy frustration. A context where you get for free spin charge separation, charge degrees of freedom that are actually bosonic, with a potential for exotic transport properties, and perhaps a new route to superconductivity. And this is just the beginning. We have some proof of principles and some theoretical understanding with lots of open questions, and in particular, open questions about how to potentially realize this in experimental settings. So we're looking forward to that if it ever has come to pass. To introduce the RVB liquid, I was told to focus really on 30 minutes of introduction and then 20 minutes of new results. So I'm trying to go by the instructions. And the idea of an RVB liquid dates back to the 1970s, where Faseka and Anderson, in the context of superconductivity, in fact, were thinking of a possible alternative to Néel order. Néel order is what happens when you have antiferromagnetically coupled magnetic moments, and the best thing you can do if you are on a bipartite lattice is to put them anti-aligned with their neighbors, and you form an ordered pattern. An ordered pattern through which transport is really difficult to occur because it would leave behind domain walls that cost a lot of energy. They were interested in easy transport and therefore, and in the context of superconductivity, and therefore thought of possible alternatives. And there is something that quantum mechanics can do when there are degenerate states, which is making them resonate. The idea was dating back perhaps to Pauling in 1930s, where they drew their inspiration from the so-called theory of resonance in chemistry. The most familiar example is perhaps the benzene ring, where you have sp2 carbon atoms in a hexagon, and each carbon atom makes 3 links with its 2 neighbors, and therefore it has to split the symmetry, makes 2 links on one bond and 1 on the other. But of course, you have 2 possible degenerate ways of doing that. And quantum mechanics, if there is a superposition overlap matrix element between these, will always prefer a coherent superposition of the 2 and lower the energy of the system. And that creates a resonance, typically drawn as a ring on the benzene molecule. The same can happen with antiferromagnetic bonds. If you have an up-down arrangement of spins, that's isoenergetic to a down-up. And if you have a matrix element between these two, nature or quantum mechanics will dictate that the ground state is a superposition, a singlet between the two, down-up plus up-down over root 2.
So here I have a question I wanted to ask you, Claudio. Yeah, so I was just, curious. So let's just say, assume you have this, RVB state, right, in each of these bonds, similar to what I sort of asked you, earlier. If you try to break up one of those bonds, with impurity or disallow some, basically like a percolation problem, right? So at what point, if you start breaking each of these bonds, at what point this entanglement, sort of start to be problematic?
I mean, I think so it depends on the state we have. This here is what would be referred to as a valence bond crystal. It's a regular pattern of these singlets.
Sure.
Generally speaking, if you're asking what would break, if you have a degenerate superposition of these, what would break the massive entanglement, you would need something that percolates across, generally speaking.
So for triangular lattice, the percolation limit is probably about 50%. If you break 50% of the bond, it would still be.
I don't remember what it is for so the square lattice is 50%. The triangular I don't remember, but
I see.
Yeah, you wouldn't like it should be robust to a fair amount of impurities in general expectation terms.
Okay, thank you.
Yeah. Then there is one subtlety that I'll mention in the next slide. One thing to notice here is that if you do this recipe of forming singlets between nearest neighbor pairs of electrons, the singlet is perfectly antiferromagnetic within itself, but so in this represented here by these thick blue bonds, but the thin bonds, the nearest neighbors across singlets, 50% are ferromagnetic and 50% are antiferromagnetic. So you have a finite density loss in terms of antiferromagnetic energy. And so the idea that Anderson and Fazekas had to compensate for this loss is to think of lattices where instead of a perfect antiferromagnetic arrangement like a square lattice, you cannot have it, like the triangular case. And then you think about a possible state that is a superposition of all possible ways of pairing up the lattice into nearest neighbor pairs that form singlets. In this case, you have an extensively many states, and it gives you an even more enhanced gain in kinetic energy between them. Yes?
Sorry for interrupting, but your screen is shaking. Do you know how to solve it?
Is it shaking right now?
Yes.
Yeah, that's true. Your screen is actually shaking a little bit. I don't know why.
Oh. It's not shaking on my laptop.
Just
let
keep
me
going.
try to stop sharing.
Yeah, try to share again. I think people can still see. It's just been shaking a little bit. Oh, now it's good.
It's actually titillating. It's actually quite annoying. Now it's stopped.
Yeah.
Is it stop? Okay, good. Yeah, thank you for pointing it out, because on my end it was perfectly normal, so I wouldn't have noticed.
Okay, yeah, keep going.
It's good now, yeah?
Yeah, it's good.
Yeah. Okay. So the idea is not only to make two spins resonate and pair them up all, but then you make all possible such configurations resonate with one another. This creates what is known as a massive superposition, massive because you have exponentially many of them in volume, in numbers of electrons, and oftentimes is referred to as being massively entangled. So if you have a state like this, then disorder would actually be quite ineffective at disrupting it. However, this superposition could have give rise to topological phases of matter, and how robust those are to a disorder depends on the nature of the phase. But that's maybe a story for another time. I just wanted to answer the question earlier, but we won't be discussing disorder in this talk. So since this idea in the 1970s, people have worked on this search for an alternative Nunez phase, which was dubbed a resonance valence bond phase. And it's important here to think about what resonance stands for, because the singlet is already a resonant in itself, but that's the term valence bond. Resonant is really the superposition of many different such singlet configurations. And compared to a valence bond crystal, the pattern I discussed earlier here, which is a regular arrangement of singlets. And the search for this liquid became quite hot when, shortly after its proposal, Steve Kivelson realized that its excitations are very unusual. They split the spin and the charge of an electron, which gives rise to the potential of new conductive and superconducting phenomena. The idea of Anderson and Fazekas was really to try and use this as an underpinning mechanism to explain high temperature superconductivity. That research direction so far has been unsuccessful. I don't know any relations that have been solidly established in that sense. However, the idea of a resonance valence bond liquid seeded research on what are nowadays called quantum spin liquids, that led to important advances in understanding how gauge theories and emergent gauge symmetries play a role in condensed matter, how topological order can be framed and understood in a context different but related to fractional quantum Hall, phenomena like fractionalizations, etc. Despite decades of searches for these systems, however, the original idea of Anderson and Fazekas of finding this type of phases in a system of electrons close to a Mott insulator proved ineffective. Instead, people turned into try and finding proofs of principles of the existence of quantum spin liquid phases by looking at how you can induce them with interactions between spins, and in particular when these interactions are geometrically frustrated. The idea is that an antiferromagnet on the square lattice has a unique doubly degenerate lowest energy state, whereas the antiferromagnet easing, say, on the triangular lattice is degenerate, extensively degenerate. That's the notion due to the geometric frustration between the interactions. Some of the initial languages with which this problem was studied was formulated by Roxar and Kivelson in terms of quantum dimer models, which led to the first proof of principle and the major discovery by Mersner and Sundi of a short-range RVB liquid phase in quantum dimer models on the triangular lattice. It was followed with more exotic and interesting systems, such as vertex models, Klein models, and others. But while the question of principle of the existence of quantum spin liquid has been largely settled, the quest for a realistic Hamiltonian and an experimental realization is still pending. And indeed, it's interesting that in 2005, Raman, Mersner, and Sondi pointed out indeed that what one should focus on is studying much simpler Hamiltonians, perhaps going back to the origin of models for Mott insulators, Hubbard model, and so on. But since 2005, little progress has followed. And 2005 is a coincidental year in several respects, as I'll point out. It'll come back twice in this talk, coincidentally. Exchange interactions or other dipolar interactions are not the only ways in which you can induce magnetic correlations in a magnetic system. It was well known since the 60s that actually, if you have itinerant degrees of freedom coupled to your moments, you can actually induce magnetic correlations taking advantage of the changing kinetic energy of the itinerant degrees of freedom. The most notable example is Nagaoka's theorem. If you have one hole in an infinite U Hubbard model, and you have a proof of ferromagnetic ground state. The infinite U Hubbard model is the simplest model we can write down, perhaps, of electrons hopping on a lattice. There is a tight binding mode amplitude T, which is essentially the overlap integral between neighboring sites that allows electrons, spinful electrons, to hop from one site to another with spin preserving. There's no spin orbit coupling here. And infinite U means that, well, U is the Coulomb on-site repulsion. In general, if you have electrons on a lattice in a simple model like this, you can have occupancy 0, 1, or 2. Two electrons can live on the same site so long as they have opposite spin. And U is the cost of having them both on the same site. But infinite U means that you forbid double occupancy. In an infinite U model, if you are exactly at half filling 1 electron per site, you have a complete insulator. This Hamiltonian annihilates that state because nothing can hop, nothing moves, and you have each electron with its own spin and nothing else. And then Nagaoka pointed out that if you remove 1 electron and you create a hole, like in site 11 in this picture here, then the hole is able to move around. Well, electrons technically hop on the whole site, but you can view it by duality as if the hole is tight binding around. And then the kinetic energy of the hole actually favors ferromagnetism. There is a simple pictorial way, perhaps, to understand this, with the fact that if you have a tight binding particle on a lattice, its lowest energy state is when its wave function is as spread out as possible. It is plane wave with 0 momentum, or if you want a standing wave, keep as flat as possible in a finite system. And this means that this lowest energy state is achieved by allowing perfect constructive interference whenever the hole hops from one side, travels from one side to another along different paths of the same length. And this is achieved on a square lattice if the spins are all the same. If the background spins are different, when you move along 2 different paths, you generate a different configuration and interference cannot happen. As a result, quantum mechanics cannot take advantage of interference to minimize the energy, does not generate a superposition, and the state costs more energy than a ferromagnetic one. Ferromagnetism, however, is not the only possible outcome. And already Fazekas, in his lectures notes in 1999, pointed out that on a square lattice, that's the obvious outcome. But if you have a triangular lattice, this is no longer true. However, it wasn't really until 2005, first coincidence with the remark by Raman et al., that Herter and Shastri really studied the full effect of this phenomenon, and it was followed by a few other papers that I'll mention briefly in a moment. What happens on the triangular lattice? Let's see it in the picture shown here. If I assume a ferromagnetic configuration as shown here, I have a whole single triangle, a hole at site 1, and these 2 electrons, site 2 and 3. Let's imagine we hop the hole around the triangle. So we exchange it. Let's go up first from bottom left to top. We exchange 1 and 2, and then we exchange 2 and 3 going down to right, and then 3 and 1 going back to left. We have hopped around. We have come back to the same configuration. But of course, in this case, if we have positive, what is known as overlap integral, so T is positive and we have a minus T in the Hamiltonian, then having an odd length loop means that the process picks up a factor minus T to the 3, minus t cube, which is negative, and you have perfect destructive interference. So the ideal case for a square lattice that led to the minimal energy of a ferromagnetic configuration is here quite bad for the system, because the particle, the hole hopping around the triangle, cannot take advantage of the kinetic energy at all. It leads to destructive interference and the process doesn't gain any energy. On the other hand, if we have antiferromagnetic arrangement of the spins like shown here, let's start, I presume you can see my cursor. So let's start from the triangle that I'm highlighting at the moment. And then let's do the same process, move the hole around. Now the spins are oppositely aligned of the two electrons. We hop once, we move exchange 1 and 2. We hop second time, exchange 2 and 3. We hop a third time, exchange 3 and 1. We got the hole back to the original position, but the two spins now have traded positions, so they are no longer the same state, and interference is not possible. This was the issue on the square lattice that didn't allow you to gain from constructive interference, but here instead it saves you from destructive interference. What now the hole can do is hop again, exchange 1 and 2, 2 and 3, 3 and 1, and finally you come back to the initial state. Now interference is possible, but you have done 6 hops, minus t to the 6, resolves the sign problem, and allows for constructive interference. So the energetic effect
in
is
all
weaker.
these 6 cases, the energy is the same, right? The exchange energy is the same, right?
Yeah.
Yeah. So it's completely degenerate. There's also
this
six
isn't exactly. It's from a magnetic point of view, it's completely degenerate. And then you ask, what kind of superposition of these states can you generate that lower the energy of the hole, the T part?
I see.
Yeah. And here you can. It's a weaker effect than ferromagnet because you have to go around the smallest plaquette twice rather than once. But you can at least gain something compared to the ferromagnetic case where you had 0 gain because you had destructive interference. This is a bit of a pictorial picture. One should do it with more thorough calculations, but it captures the essence of the mechanism. And the mechanism tells you that if you put your electrons on a triangular lattice with infinite U Hubbard Hamiltonian, and you poke a hole, you remove one of them, and you look at the lowest energy state, it will not be the ferromagnet. Actually, the system will try to develop antiferromagnetic correlations. While it was noted already, as I mentioned, by Fazekas, back in the days, it wasn't until Herter and Shastri that this was studied as a many-body problem. Fazekas' notes limit the discussion to single triangle. Herter and Shastri started to say, okay, what if we have a triangular lattice, an extensive system? What does come from this favoring of antiferromagnetic correlations, which are in fact frustrated on the triangular lattice? And what they showed is essentially that the system behaves as a Heisenberg antiferromagnet on the triangular lattice, which order by disorder leads to a 120-degree order at low energy state, and then was later confirmed and studied further by Sposetti and Lisandrini's paper in 2014-2017. And the literature more or less stopped there in these systems. It was picked up in parallel by Zhang. Christian Batista was involved in this work, again, in terms of what kind of pairing mechanism you could have in the spirit of superconductivity, searching for superconductivity mechanisms, but then it stayed dormant. Very recently, there has been a resurgence since 2021 of this type of problems in cold atomic systems with Demler's group, Liang Fu at MIT, and Ashwin also, Vishwanath has been working on this. And there are a few papers that are not here. This is not quite a review for that matter. And then some interesting work that I'll actually discuss by Kim in 2023. And I'll come to that in a second. So, okay, I could have said it here because that's what I just said without pointing at it. Conventional antiferromagnetic order in 2D on the triangular lattice. Not much else was studied. Triangular lattice is not the only frustrated lattice there, but somehow studying Kagome is a lot harder. In fact, Kagome-Heisenberg antiferromagnet is to some extent still a question mark about its ground state quantum mechanically. So no one really went there. The only other work that was done by Kim in 2023, a graduate student of Steve Kivelson, but this was a single author work, did it by himself very cleverly, and went to investigate this problem on something close to Kagome lattice. Kagome is very difficult, but what he did is he built instead a Husimi cactus of corner-sharing triangles. Husimi cactus is a decorated Cayley tree. What you have, maybe I can illustrate it from the figure here. You start from a central site indicated by I here. You put 2 triangles attached to it, and then you have 4 remaining corners in total. And at each corner, you attach another triangle, 1, 2, 3, 4. And then again, at each corner, you attach other triangles. But you build a structure that is a tree expanding out in space, in hyperspace to a large extent. And there are no more connections that you create. The only connection is how you grow it, right? So for example, if you want to go from out here to out here, there are no connections without coming back to the origin and going back out, right? That's a property of the trees. It's a trees made of triangles. In a tree, there would be no loops whatsoever. In a Husimi cactus, the elementary loop, the triangle, exists, and there are no other loops in the lattice. So it's clearly, well, it's generally not something realized in nature, or not easily realized in nature, but the absence of other loops makes theoretical calculations easier. And in fact, Kim was able to find something truly interesting, but demonstrated that if you take the same problem, infinite Hubbard model, on this funny lattice, and you remove 1 electron and ask what's the ground state of the Hamiltonian, the ground state takes a very interesting form, which is drawn pictorially here. Imagine the hole is at site I, and then you pair up all the remaining electrons with this in nearest neighbor pairs, as shown by these pinkish thick bonds. Notice that once you fix the position of the hole, the pattern is given. There's nothing, no freedom left in the system. And then he was able to prove mathematically, very interestingly, that the ground state of the Hamiltonian is actually the equal amplitude superposition of all possible hole positions on the lattice of these states. And it's an interesting dilemma of what one would call this, because if we fix the hole position, there is no degree of freedom. The valence bond pattern is fixed, and you would be tempted to call it a valence bond crystal. On the other hand, you quickly, well, not so quickly, but you can realize that if you move this hole here and you move the corresponding bond here, and then you keep going, you keep rearranging the configuration, and it just up to rotation and translation, it maps onto the same configuration you started with, and the hole is free to move. So the hole is actually deconfined, which is remarkable, and it is a special property of a Husimi cactus, if you want, that you have simultaneously something that looks like crystalline order in the background and completely deconfined excitations. That was a very interesting result, but short of a regular lattice, there was no resonant process in the system other than the motion of the hole itself. Right? And what we did, we were doing it in parallel when we came to know of this result, and then we took the problem to 1 step up in dimension. You know, like sometimes luck hits. You would say that if you go from a complicated problem in 2D and you make it to 3D, usually there's no chance in hell. This time, it was a lucky shot. There is another option for triangular lattices that are frustrated, and that is the pyrochlore lattice. Right? It's a lattice of corner-sharing tetrahedra, and it's made of triangular faces. And what we wanted to understand is what the effect of these counter-Nagaoka antiferromagnetic correlations would be on a lattice of this sort. And what's special about this lattice can be already understood at the single tetrahedron level. At the single tetrahedron level, the infinite U Hubbard model with 1 hole is essentially a 3-electron problem on 4 sites that are fully connected, right? As shown here. And the Hamiltonian can almost be diagonalized by hand, and you can quickly realize that the ground state does something quite unusual. Two electrons in this figure 2 and 4, at site 2 and 4 form a singlet. The hole at site 1 in this illustration is able to resonate with them along the plaquette 1, 2, 4. And site 3 is completely just a spectator sitting on the side. Any attempt to make the site 3 hop onto the whole site, which would be allowed, generally speaking, an electron hopping on a whole site is allowed by the Hamiltonian, is completely killed in this system, in this problem, by destructive interference, somewhat miraculously. And you can literally write down the Hamiltonian by the ground state by hand. You can. It's going to be useful for later, so let me actually state it. You can construct a singlet creation operator, the dagger ij, 1 over root 2, c dagger up, c dagger down, minus c dagger down, c dagger up. With these are spinful electron creation operators at two sites I and j. Notice that thankful to the anti-commutation properties of electronic operators, the dagger ij is equal to the dagger ji, so there is no issue about ordering, direction, etc. And because they are two electron operators, these d's commute with one another and commute with c's. So it's particularly simple to write the ground state wave function as, in the case illustrated here, c dagger 3 up, an electron sitting there and doing absolutely nothing, and the superposition of the three whole possibilities, d dagger 1, 2, d dagger 2, 4, d dagger 1, 4. And what has happened is that your hole hopping around a triangle would have killed itself by destructive interference because of the minus t hopping. However, the electrons 2 and 4 forming a singlet have effectively attached a pi flux to this plaquette, enabling the hole to hop around it resonantly. Right? So you have this flux attachment style physics of the two electron singlet allowing the hole to gain the kinetic energy, maximal kinetic energy that it can. Right? The hole is hopping on a ring. The ring has connectivity 2. The lowest energy is minus 2t, as you expect from a simple tight binding Hamiltonian. Of course, this looks beautifully elegant, simple, etc., but it's a single tetrahedron, and one would expect that it would fail as soon as you're trying to build a lattice from this elementary unit. And this is really the surprise of all of this physics, the fact that it absolutely doesn't. On a full lattice, shown a portion of it here, something somewhat spectacular happened. The hole at this site is able to resonate simultaneously with two triangular plaquettes where it shares a singlet with the top tetrahedron and a singlet with the bottom tetrahedron. And it's able to hop freely around these two triangles. And if it hops, let's say that we hop the hole here and the singlet goes here, then it's able to resonate with this face. And so the hole is able to move on a corner-sharing triangular lattice, which is embedded in a pyrochlore background. And the embedding is completely dynamical because as the hole moves through, it moves around the singlets, and therefore it changes the triangular garnet over which it moves. But at any instantaneous point where the hole is somewhere, the hole is able to hop around two triangles and therefore has connectivity 4. Right? There's 4 directions it can hop in. And therefore, lowest energy is minus 4t, exactly. Not approximately, not with a correction, it's exactly minus 4t. The singlets next to the hole again do the same trick of attaching a pi flux to that triangular face and allowing it to gain the full kinetic energy without any corrections. Interestingly, and again, this is the third coincidence in years, this minus 4t was observed by Didier Poil-Blanc in ED simulations on the corner-sharing triangular lattice back in 2004, which are remarkable because at the time, well, he was a master of exact analyzation and numerics and was able to do system sizes that we still have a hard time getting to today without his expertise, put it that way. And he showed that you get exactly minus 4t with a single hole, minus 8t with two holes, but we'll come back in a minute. He suspected that an exact number in physics doesn't happen by chance, but there would be an underlying mechanism, but didn't have an explanation for it. And it's a year before, in a sense, the framework, the beginning of the framework to understand this oddity was seeded by the paper by Herter and Shastri. What kind of wave function arises from this is a wave function where you have a hole on a site and every other electron is paired at nearest neighbor level in a singlet, and then you have a superposition of all possible singlets and a superposition, of course, of all possible hole positions. It's the perfect exact nearest neighbor RVB liquid that one could dream of, that Fazekas and Anderson would have dreamt of at the time. And this can be...
Claudio?
Yep.
Yeah, I was just curious if you go back one slide. So are you saying that this configuration is distinct from that on this cactus problem, and that like there's not, if I fix the hole at that origin, are now the singlets, is it still uniquely defined? You know, the configuration as it was in the cactus, or now it's degenerate?
Every time you fix a singlet, you have exponentially many configurations in the volume of in the number of electrons in the volume of the system.
Got it.
So it's an interesting chicken and egg question, because of course the superposition is generated by the hole. If the hole was fixed to begin with, there would be no superposition. But if you imagine a Gedanken experiment where you allow the hole to move about and set up the superposition, and then you fix the hole, the superposition even is a massive superposition, is a massively entangled state.
Sure. Okay. Got it.
So this is the important difference to the Uzimi cactus. You can do also a Uzimi cactus of tetrahedra, which becomes slightly harder to think about, but not too difficult. And again, you would have the same problem where you wouldn't have this extensive degeneracy. It's important to be on a regular lattice to achieve that, and it's really what gives you the RVB liquid nature.
Got it. Thank you.
You're welcome. Interestingly, this is an exact analytical result where we can prove paper and pen with one hole in the thermodynamic limit. The proof actually spans two parts. One is you can prove the ground state is a lower bound by minus 4t, and then the lower bound is met by this superposition that formally is written here is the sum over all hole positions, sum over all possible singlet arrangements, of which there are exponentially many, of the product of the singlet creation operations over all of these nearest neighbor pairs acting on the vacuum, right? If you want to see it formally, or hopefully what I said hand-wavingly was clear enough. It is the exact short-range RVB liquid ground state that people would have dreamt of. Interestingly, the beauty of the result doesn't stop there. It's not only exact in the thermodynamic limit, it's exact for any finite-sized system with periodic boundary condition. There are no finite-sized corrections to this system. The ground state remains minus 4t, hence Didier's result back in the days when he did ED, of course, was finite-sized systems, and it was exactly minus 4t, not minus 3.99 or anything else. Interestingly, if you put a hole in finite-sized system, you necessarily have an unpaired electron, which therefore leaves behind an unpaired spin. And you would think that that could matter, but it turns out that it doesn't. It's perfect spin-charge separation, and the hole is unable to ever see this lone spin because of the same destructive interference effect that I mentioned earlier at the single tetrahedron level. In fact, you can even put two holes in the system, and you realize that the ground state energy is exactly minus 8t. The ground state is unique. In this case, here you have the unpaired spin position that gives you some trivial degeneracy. This is unique. The ground state wave function is again the equivalent superposition of all nearest neighbor singlet states. And now there is a subtlety about the tetrahedron without dimers being immaterial when you write it in electronic states. Maybe this is a higher level comment that I can explain for those who are interested in understanding more of the details. It's quite exquisite, the fact that the energy goes to minus 8t. It means that the two holes are completely oblivious to one another. They're unable to see one another. And it's worthwhile actually taking a moment to think and appreciate what's happening here, which seems something somewhat magical or fine-tuned. But in fact, it's simply the following property. When two holes come together in a tetrahedron, shown like somewhat pictorially here, the other two spins the remaining two spins are forming a singlet between one another. So the hole 1 is able to resonate with 2, 4. 3 is able to resonate with 2, 4. But beautifully, they're able to do it at the same time. Because if you swap 1 and 2, for example, then 3 is no longer resonating with 2 and 4, but resonates with 1 and 4. So it always continues to resonate with a triangular face. It just changes as they move and the hole hop around. And the holes are obviously hardcore objects. You cannot have two holes on the same site. So in principle, you would expect some excluded volume phenomenal corrections, because 1, 3 is not a hopping channel, but in this system is perfectly destroyed by destructive interference. And so they really don't see one another and don't affect one another in any way, and it's minus 8t the energy. Of course, this beauty, this elegance stops at 2 holes. If you have 3 holes, well, they begin to see one another because they no longer afford this perfect destructive interference. But so we generally we see numerically, and we generally expect some kind of free-body scattering corrections to the picture when you go to finite hole density, and the wave function is no longer writable in paper and pen, or at least not that we have found so far. So what do we know to date about this ground state wave function? Something, but perhaps not as much as one would wish. It's true that we have an exact solution, and it's true that we can write down analytically the ground state, but unfortunately, it remains an interesting phase of matter. An RVB liquid is an extensive superposition of electronic states. It means that you have, if you want to compute something, you have to compute exponentially many electron states, and it's still computationally challenging. So far, we have done some analysis. We hope to be able to push it further. One thing, obviously, is to look at the structure factor. We did it for a system of 32 sites. So one should not look at these color maps in any significant way other than comparatively. We did the same system for a Heisenberg antiferromagnet, a quantum one, QHM, and a classical one, CHM. And these are HHK plane and HK0 plane, which are typical too that people look at. What one should take from this is A, don't look at it too seriously. B, we don't see sharp features consistent with the liquid nature. And D, or C, they don't look immediately like a Heisenberg antiferromagnet. So it seems that maybe the correlations are a little bit different, but really too small of a system size to make strong claims. Another thing we did is to look at the hole-hole correlations when you have 2 holes in the system. And this is shown in the middle plot here as a function of hole-hole distance. The dashed bottom data are for 32 sites system, and the top ones are for 16 sites system. So we can actually just look at the 32 sites really. And what you can see, of course, they are hardcore, so 0 at 0, that doesn't tell us anything. The other data tell you that they are flattening out pretty quickly. They are perhaps slightly repulsive at lattice distance, but they are largely deconfined. There is something else very interesting that we learned from this, and the fact that if we do the hole-hole correlation, or consider a single hole and a leftover spin-on that I was mentioning earlier is fixed somewhere in the system, and we look at the whole spin correlator, they are exactly on top of one another. The whole spin are the dots, and the whole hole are the x's. And you see that they overlap perfectly. And if you have a tight binding problem where distinguishable particles and indistinguishable particles have the same correlations, the most likely chance is that the indistinguishable particles are actually bosonic. And in fact, we do some bosonic modeling that I'll flash very briefly, shortly, to confirm that really these holes get dressed by the spin liquid background to become bosons. And this is pretty interesting and important. They are fermions to begin with. You're removing an electron from a lattice. You are injecting a fermionic degree of freedom, but the holes get dressed by the background to become bosonic. And the last bit of information here is that what happens if you add exchange interactions? You make U not infinite but finite, and then the spins can talk to one another directly through exchange. And then you can ignore the right panel here is for the Nagaoka effect on the square lattice for comparison. The counter Nagaoka effect, there is a window shaded in gray here of stability that gets larger if you go from 1 hole to 2 holes to 3 holes. So it's suggestive that this system is stable at weak enough interactions and finite density. But again, we're looking at small system sizes. I wouldn't make too strong of a claim at this point. Further work is needed, but it's pointing at least in the right direction, in the promising direction. This is the bosonic model I was mentioning. If the holes are bosons, we can assume that they are just hardcore tight binding on the pyrochlor lattice. And there may be, we add for fine-tuning some nearest neighbor repulsion that is our only tunable parameter. The hopping is effectively 2T/3 because there are only 4 out of 6 directions where the bosons can hop, where the holes can hop in the original lattice, whereas these bosons can hop in all 6. So we need to rescale the hopping term. And by doing a fit on the interaction V, this was the work done by the undergraduate student Daniil, you can see that V is slightly attractive, if anything, and then the exact result from the previous page, previous slide is in the pluses here. The effective model gives you the crosses, and it clearly shows that you can capture the behavior very well with just a nearest neighbor interaction. Interestingly, then Daniil went on to do some field theoretic calculations to get the some ladder calculations to get the scattering length in units of the lattice spacing, 0.3, and this suggests that there is no binding, and therefore condensation of these holons is possible as bosons, and that would lead to some kind of chargey superconducting transport phenomena, which would be exotic and interesting to explore. It relates to an old dilemma that was discussed by many people, among which Steve Kivelson in one of the perhaps nicest PRL titles I'm aware of, 2E or not 2E, flux quantization in the resonating valence bond state. How much time do I have still? Approximately?
I have 5 minutes.
Okay, perfect. Yeah, that's plenty actually. Mostly what I wanted to say is done. Maybe how do we understand, how do we hope to go forward in understanding this system? What was done in the past in understanding RVB liquids was proposing these quantum dimer models that I mentioned earlier. What those do is that you assume the singlet is now a degree of freedom, a thick bond on the lattice, and you assume they're orthonormal, and you build a model physics out of these dimer configurations. And this was very powerful as a tool to tell us a lot about this system and create this proof of principle of existence of quantum spin liquids on the triangular quantum dimer model. However, if we then replace each dimer with a singlet, what were originally orthonormal states become now linearly dependent. And this brings about some issues in discussing the problem that are particularly prominent on the pyrochlor lattice. Ideally, what we would like to do is study the problem without holes and see what the spins do. And then once we understand that spin liquid, we can try to understand how its excitations couple to holes when you remove a spin. However, if you try to follow this route and you take the equal amplitude superposition of all nearest neighbor singlet states on the pyrochlore lattice, that equal amplitude superposition vanishes exactly, which is something that took us by surprise, highly unexpected, because it doesn't on other lattices. And eventually Daniil did some beautiful work using the statistical mechanics of graph theory of objects called trees and forests, and was able to prove it mathematically. This tells us that basically the zero hole limit doesn't exist. It's not a problem experimentally because low doping is as good as zero doping. Actually, achieving exact zero doping is probably more difficult than low doping, but it's a problem theoretically because the holes create this state and are in some sense needed. They are the simplest example of an open boundary condition that allows this superposition not to vanish. And then Daniil went on to actually understand this in terms of this tree graph theory and was able to formulate a new, perhaps, idea of how to discuss this massive superposition, not in terms of dimers, but in terms of configure Fock states of electrons or up and down spins and statistical mechanics of graph theory. It's work in progress. We are hoping that it will lead to understanding of correlations in a new language, but it's as I said, to be seen. It's ongoing effort. Okay, so what's the outlook and open questions about this? I stress what we found is a remarkable exact solution of a strongly interacting many-body problem that is beyond what's bread and butter. It's a non-Fermi liquid behavior that hosts spin-charge separation. This means that large U and small u behavior are not continuously connected. In fact, small u behavior predicts something different. And so we cannot get to this perturbatively. We would like to understand better the spin correlations, whether they hide some kind of gauge symmetry, whether there is a topological field theory capturing them. Larger systems are needed, either advancing this graph theory that Daniil has started to investigate, or perhaps finding clever enumeration ways to compute this exact ground state. We would like to find more evidence of the stability to finite hole density, perhaps an argument based on three-body versus two-body scattering that I was mentioning briefly earlier, and two interactions, exchange interactions that are expected at finite U. What about candidate materials? There is the platinum group pyrochlore oxides, iridates, ruthanates, have an interesting phenomenon. The iridium site has essentially spin a half emergent degrees of freedom, and then if you dope them to 4+, they become spin 0. So they are sort of the ideal setup, and pyrochlore, very regular pyrochlore lattice. However, they have strong spin-orbit coupling and anisotropy, which are not present in the Hubbard model we used. Therefore, we would need to check whether that throws away all of the physics we are interested in. Copper 2 compounds and manganese are ideal if we want to find models that are well described by large U isotropic Hubbard Hamiltonians. However, and they do grow in some pyrochlore systems, but they tend to be heavily distorted. So we would need to understand again what the effect of distortion, how much we can afford in this system before the RVB liquid prediction is gone. Every result that I stated, I framed in the language of the pyrochlore lattice, but it works for any corner sharing arrangement of tetrahedra, which includes the checkerboard lattice, interesting, a planar structure, provided that the hopping across the diagonals is the same strength as the hopping along the sides of the squares. And of course, that's not usually the case, even if one could realize a checkerboard lattice in nature. And so we would like to study better what happens as a function of anisotropy, how soon you depart from this physics if the diagonal, so nearest neighbor T and next nearest neighbor T prime differ. This was the work done by Paul Blanc in 2004. And then once we think about 2D systems of this sort, maybe implementation of synthetic quantum platform in terms of building more than finding in nature this type of system could be interesting, be it superconducting qubits or cold atoms or trapped ions setup. So with that, I just want to close that we hope we have taken the first step towards what might become a paradigm shift in terms of searching for new other liquid phases in quantum magnetism, from geometric frustration to kinetic energy frustration. This was done in realistic Mott insulator Hamiltonians. There are admittedly infinite U Hubbard and 1-2 holes where we can say something reliably, but still more realistic than 4-body, 6-body interactions or vertex or dimer models at this point in time. So they have some element of promise, and they are on experimentally accessible lattices. After all, at the very least, the Pythagore lattice is decently common in nature. The fact that we have an exact ground state is rare and cute and elegant in its own right, and gives us again another angle, even though there's no free lunch theorem. Studying numerically that exact ground state is still a tall order. But we hope that it'll open a way to a new playground to realize RVB, quantum spin liquid behavior, finally detected in nature. And with that, thank you very much for your attention, and I welcome any questions.
Thank you, Claudio. So I have a question immediately. Yeah. So okay. Yeah. Let me ask. Okay. Maybe Steve asks first. Yeah. Steven. Yeah.
Oh no, that was just I don't know why.
Oh,
you
you
sent that
pop
on
it.
the screen.
Yeah. So I have a question. So basically, I mean, how important is the quantum number in terms of spins? I mean, you basically think about you have to have a ferromagnetic exchange interaction, right, between the bond. And does it really matter whether it's a spin of a half, spin 1, and so on and so forth? In your picture?
We haven't tried to investigate other spin values. I think it's important. So the spin what's important is the singlet nature of the bond that gives rise to this pi flux as you hop around.
Right.
And now, if you had spin 2, but you create somehow a singlet between plus and minus 2 or plus and minus 1 within it, that would be okay, because it's the fact that as you hop around, you pick up that minus sign because
right.
the superposition changes order. That gives you the pi. So it doesn't hinge strictly on the spin half, but the spin half is the most natural context where a matrix element will induce something that is AB plus minus BA.
Right. I see. So this basically, I mean, if let's say you wanted to look for candidate materials, I mean, like you said earlier, iridate is problematic, right? Because of the very strong spin-off coupling. So then you basically have to look at copper or some sort of a rare earth material, where the but those most of these protocols are sort of a, I mean, is it really required to be, I mean, metal, right? For this case to happen, right? Most protocols are sort of strong insulator. I mean, slight doping. You think it will change it into a metal or? Well,
so what we have is a Mott insulator.
Right.
So if there are strong band insulators, there's a problem. But if Mott insulators is fine.
Okay. I see.
So again, so the fact that they are insulators to begin with, then it's not necessarily problematic. We would have to see under the hood what kind of what is it that makes them insulating.
Mm-hmm. I see. Yeah. Okay. Are there any other questions from the audience? Okay. Great. Yeah. Thank you very much, Claudio. Yeah. Appreciate this very much.
Pleasure.
Yeah. Thank you.